time this happens.
This coming session is going to be focusing mainly about modeling line profiles. So I'm really excited by the set of three talks. So we're going to start with Baptiste, who's going to tell us about doing it in the sun.
Thank you, Suzanne. Hi, everybody. I guess everything is fine. Can you hear me online also too? I guess it's fine too. Okay. So, hi, everybody. I'm Baptiste. I'm a postdoc student, not longer student. I'm a postdoc working with Suzanne in the ERC project. And I'm very happy to be here in person to tell you about my work in modeling the stellar activity, but directly in the CCF. So when I say line profiles, I mean CCF, but you know there are some extensions possible to polarize line profiles. I will mention this a bit later. And this is a really quick reminder because everybody here is familiar with the context. Just to say that over the past few years, we've been really trying to include more and more constraints in our data sets, like to leverage basically the wealth of information, both in the line profiles, but like we're going on further, just in the full spectra to model and filter of this stellar activity contribution. And we have now plenty of great data set, even though there is, of course, still work, as we've been discussing just before. We have like plenty of great data sets to do the science with, and just need to find a way to filter the stellar activity signals. And in this talk, definitely choose to work with the CCS because they're a good trade-off between having enough data, enough precise information about what we want to model as things stand. And for stellar-like stars, we have very, very good CCF. We're definitely very optimized for this. So it works relatively fine if we want to model the solar CCF. And I represent basically two methods. I choose to divide this into basically two parts. One kind of method that's data-driven, where we basically don't know what we model. We just want to separate activity from planet-induced signal, and the other one, which is completely physically driven, it's called Doppler Imaging. You might have heard about this, but I will definitely try to explain and spend some time to make it clear. And yeah, the HARPS-N solar data set is actually the best data that to start working with if you want to implement a new method on this. And just like a very quick slide about the sun that we already know that the sun is being monitored. Like there are plenty of distributions that are monitored very icons around the sun, like the intensity, but also the magnetic fields, polarized and unpolarized. So there is definitely room for doing exciting science with this. And of course, on high resolution spectroscopy, we have, of course, the project that were mentioned today. There is also EXPRES. I don't know exactly if you want to say something after. And there is also Pepsi and Chris that has not been mentioned, but it's because this instrument observes the sun in polarimetric mode. It's very low spectral coverage. So it's very tiny wavelength range, basically. Okay, so our input data set is the HARPS-N solar observation, and we just decided to build a kind of more or less realistic data set from these observations. And to do so, we just select lastly processed data with EXPRESSO DRS. And we want to select the data where basically there is no cloud obstructing the sun, so the data with a very good quality as assigned in Andrew's paper. And we want to be more or less consistent, homogeneous in our way to look at the sun. So basically we want to have the sun at the zenith at every observation. And when available, we just average 3 consecutive 5-minute exposures to build our time series of CCFs. And the end, like we have 664 observations with a good signal-to-noise ratio. And as I told you before, we just work with the CCF. So these are typically the CCF in a color-coded matrix. So this is a sequence of CCF. So you have the wavelength axis here in velocity space and the epoch here on the x-axis. And once we have this aligned data set, so using GP, then we can just inject planets in the data set to build some kind of input data set. So the very fiducial case is just the data without any injected planets. But then we create 16 other data sets where we inject in each data set 1 planet with different orbital parameters. And we try just to span a relatively broad parameter space without building too many data sets because Doppler imaging is very slow. So we want to start by kind of representative, but not too much time consuming input data sets. So we build basically 17 data sets using this parameter space. Okay, and now I'm going for the first method that I wanted to introduce, but I will go fast because it's kind of a scalpel-like and a Doppler constraint PCA framework, which is being just applied basically to the CCF. So it's very easy. You start by the Taylor expansion. You could expand it further if you want to define some indicators. And you just want to invert this shift here that you have. So this basically, you say that you observe CCF at just the reference unspotted CCF, which is like your standard line profile, plus some Doppler shift and the first derivative of the CCF. And if you invert this and you do some just work to keep on being on the CCF space, you can just extract Doppler time series of CCF that are driven by the Doppler shift in your spectra. So basically, the time series of CCF will be only, the variation in this CCF will be only dominated by the Doppler component, shifting all your profiles. And so if you decide to subtract this CD term to your row CCF, then you have some CCF that are theoretically only driven by shape variation. So you basically, like in the scalpel case, except that without working with autocorrelation function, you work with just a Doppler subtracted CCFs. And the next step is just that using these CCFs that are supposedly extracted from the Doppler component to define the basis to project our RVs on and separate it between shape and shift. And this is what we do, but before doing this, since our shape-driven components also include noise, you basically want to reduce, if possible, your dimension space, and you just apply a PCA method to reconstruct a basis which is more or less noise-free, using only the first component that includes multiple variants. I'm not going very further on this point. I'm just saying that this ongoing work, and to select the number of components, we've been just doing tests on the recovery of the planets, and we are seeing that as long as you're not going on too extreme case of the number of components that you want to select, you're basically able to have very similar results. So it does not really impact much your results. And okay. Oopsie. So there is a button to quit, actually. Okay, perfect. And these are the results. So on the x-axis is the different case that I'm considering with the parameter space here explored. So what mostly interesting is like you have on here the periods. And here is the relative errors that you have on your semi-amplitude of the planet injected. You assume that your ejected planets are basically circular orbits, and that you know the ephemerides. This is the very first case, but on the second case, you can just try to randomize the parameter space and make kind of a systematic, integrate this framework into a parallelogram and basically search for period maximizing the likelihood in the data. But this has not been done yet. I just wanted to say that basically we demonstrate scalpel is exactly similar and we have good results, and we want basically to use this as a basis to define new indicators for the GPRV project, for example, or to explore further what we can say about this time series of CCF that are dominated by shape-driven variation without, and compared to those that are dominated by shape-driven variation. Yes?
Can I ask something?
Yes.
Then, for this, every couple of points, the only difference is the phase, and it always goes up. Can you explain this?
One. That's true. Not here. No, not here. Haha. That's true.
Almost every case.
That's true. Maybe you should try with another phase just to see if it's linked to the choice of the phase. Basically, the phase that we use is 0.33. We just wanted to do something which is not directly harmonic of the first phase that we want to use. That's a good trend. That's a good question. I forgot to mention our results are in black here, and the results, if we did not apply this framework, are in red stars here. So we see that we are most of the time quite close to the 1 sigma line. And the fiduciary case is if you apply the component without any activity. Okay, that's a good question. So I just wanted to prove, to talk about the proof of concept for this first method, still work in progress. And the thing I've been mostly working on lately is Doppler imaging, but trying to apply this to the sun directly. For those who are not familiar with Doppler imaging, it's always quite long to explain. So in Doppler imaging, what you want to say is that if you have very fast rotating stars, these are your CCF here, and you know that the position of your distortion of your light profile reflects the position of your spot at the stellar surface. So if you use this in Doppler imaging, you want to basically invert the time series that you observe of CCF into a distribution of dark and bright inhomogeneities at the surface of the star. So what you actually do is that you model your star into many cells, and for each of these cells, you have a local line profile, which is basically a CCF, right? So if you're here, like in the middle, your local line profile is just a CCF like this. But of course, if you go toward the limb of the star here, your profile will be Doppler shifted, weighted by the limb darkening law, and also projected onto the line side because of inclination. What you do in Doppler imaging once you have this star like this is you just integrate over all the stellar surface and you build profiles that can be basically compared to your observations. You also convolve by the instrument profile and stuff like this, but basically you build CCF that can be compared to your observations. So if now you say that for each cell here, you have a relative brightness coefficient, that could be a spot if it's like lower than 1, or could be a plage if it's greater than 1. You can just include this to your model and build spotted surface and have the corresponding profiles that could match your observations. So what you do in Doppler imaging is the inverse process. You have your observations and you invert them into a map of spots and plage, and you basically try to add them. You add them until your profiles, the synthetic profiles, must match the observation at a chi-square of 1 typically. But this is very degenerate, right? Because you have many maps that can reproduce as well your profiles. So what you do is you impose a regularization condition, which is typically, in my case, a maximum entropy regularization. So that means that the final map is unique and is the map with the minimum amount of information on it. And the information is just like the amount of spot coverage, basically. Okay, so just an example on a star other than the Sun, Ayumi. It's a very young star, rotating quite fast, and we have results like this. So these are the median subtracted CCF, and you invert this basically into this kind of distribution. So in brown you have the spots, and in blue you have plages basically. And these are basically the same. Here it's a flattened polar view. It's just more convenient to see everything. You have like the pole at the center, and around here the black circle is the equator, and you have like the 60 and 30 degrees parallel here. And we just indicate the observations around the stars in the unit of stellar phase, but it's basically the same. So it's working well for Ayumi. And we can even do something a bit further. It's like saying, okay, we have something that model the activity, which is Doppler imaging. What if we include a Keplerian signal in it? So when I say this, is that basically with Doppler imaging, we're able to reconstruct our line profiles up to a given level of chi-square, which corresponds to a level of entropy, spot coverage. If you say, okay, no, I fix my spot coverage to my best fitting spot coverage without any planet injected. What you can do is like saying, okay, how will my chi-square value change if I change the parameter space that I explore in my model? So if I inject a planet a priori in my profile for different values of Kp, and if I reconstruct my profile for each of these values of Kp to a different, to the same value of spot coverage, my chi-square will change because I changed something in my model. And in the end, you have kind of a distribution of chi-square, and you can see if injecting planets to your model improves or not your fit. And this is what we see for Ayumi, and we're able to detect mostly planet C here, and to have results that are entirely consistent with the results of the GP, multi-GP analysis presented by Norbert yesterday. But I invite you to see this paper if you want to know more. And if you want to apply this to the Sun, it starts to be quite complicated because it's already quite complicated like this. But if you want to apply Doppler imaging to a slow rotator, it starts to be very complicated for several reasons. The first one is if you don't have ID sinai, then the resolution of the features that you want to reconstruct is very low. On the other side, and which is kind of the same, if your profile is not really large, then the distortion induced by spot are not very well constrained, and you need extremely precise observations. And the last thing, which is the most complicated thing, is that when you have a fast rotator, then your profile that you see, your CCF, is just the rotation of the star. But if you have a slow rotator, you start to have also the thermal profile and stuff like that you don't fully master, that enters into consideration. And you basically don't know them. So if you just assume a random profile, you will reconstruct nothing but systematic noise. So the first 2 points are basically well are basically covered by the HARPS dataset because we have both a dense coverage of the stellar cycle and precise observations. The last point is a bit more complicated. I will talk about this just after. The other point, which is a bit complicated with Doppler imaging, is that stellar activity evolution is not included in the code. So basically, you assume that your star is the same, the activity is not evolved. So if you apply Doppler imaging to all data set, you reconstruct nothing also. So for this second point, it's quite easy. Since the observation strategy is very icon-dense, you can just select data sets with enough data point and enough phase coverage and build sub-data sets. We will build, for example, 14 data sets here. For the first point, the fact that you don't really know the profile to reconstruct, we are forced to come up with some methods that are a bit more sophisticated, which means that basically we apply our Doppler imaging code to a certain level of chi-square, which is very high. Then we subtract the median difference between our synthetic profile and the observations, and we repeat the process until the median difference is basically flat. Yeah. And if I pass on this, I'm happy to answer questions on this if you want after, but this is typically what we get on one solar rotation cycle. Spot coverage, which is of course very high, but is what we want in Doppler imaging, so there are a lot of degeneracies. And this is the map that you obtain, and from this kind of map you can just compute local synthetic profiles and have your RVs that you compare to the observation. And you see that we have residuals that are quite low here. And of course now, we want to do it to all data sets, and you have these kind of observations. It's quite interesting to see that from consecutive observations, you have quite the evolution. Right? You can see the evolution of the activity. But we didn't want to see if we reconstruct something that looks like actually something on the sun, which we wanted just to focus on the RV as a first step. And now a second step, and we will see later, will be to actually go and see if we are able to reconstruct something that is actually on the sun. This is the RVs that are obtained. So in red, basically, you have the RVs that are obtained from Doppler imaging, and in black, you have the RVs that were selected, and in gray, just like the full RVs of the sun. And you see that, yeah, so basically each set of red data points is like a stellar surface. And you see that in the end, we have residuals that are, again, quite low with Doppler imaging. It's because we construct each cycle independently, so we tend to reconstruct quite a lot of small structure with Doppler imaging. And last but not least, the goal of this, the metric that we want to look, if we want to use this method as an activity filtering method, is are we able to recover the planetary signal in the method? So first point, if you just say, I apply Doppler imaging to the CCF without subtracting the planet, and then I look at the RV's residuals and I try to search the planet therein, you have no chance to get the planet back. So you're forced to do a kind of simultaneous thing where you include the planets directly in your Doppler imaging code, exactly as I was telling you before. You fix the amount of entropy of your reconstructions, so the only thing that varies is the chi-square. Then you have a grid of planet semi-amplitude, and for each of these semi-amplitude, you reconstruct your stellar surface. You have a chi-square distribution, and you just do chi-square statistic and estimate the planet parameters. Long story short, it works quite well, actually, because we're able to recover most of the time the planet semi-amplitude, assuming that we know that the planet transit and we know the ephemerides. Where we lose the planet is basically when the orbital period of your planet is basically similar to the orbital to the rotation period of the star. And this is quite expected because in Doppler imaging, everything is based on the unit of the phase. So if your planet is also in one phase, that cannot work. But its results are quite promising. The only problem with this approach is that you're forced to do the reconstruction individually on each cycle because the activity evolution is not yet included in the eye. Okay, just about Doppler imaging, as I told you, now we have maps and we reconstruct spots at the surface of the star. It's not exactly what is happening, what dominates the RV variation of the sun. So it could be very interesting to try to include, other phenomena using a physically motivated framework for this. Can you shift locally your profiles to account for the inhibition of convective blue shift, stuff like this? With the code that we're using, we can also investigate the present differential rotation and even the magnetic field. So small-scale magnetic field, if you want. So that's why the SDO data are definitely great to explore. with. I can also recommend you to attend the tutorial for Rodrigo Luger if you're interested, which I'm sure you might mention this kind of issues, and hopefully maybe some how the GP framework could be maybe used to account for this evolution in the Doppler imaging code. What about spectropolarimetry? Yeah, so this is for future. And yeah, this is the take-home message. And I think that I leave you with all this. It's basically all this what I told you. And yeah, last but not least, just mention karaoke. Sorry. Karaoke still have 6 or 7 places, so please let me know if you're interested. And see, like some people are shy, but that would be great. Come on. Voilà. Thank you.
I see one question in the back, and then Lily as well. So, Jen.
This is super cool. For the AU-MIC results, does there happen to be simultaneous like test photometry that you can compare with and see if there's consistency between your reconstructed surface and what we see in the photometric results?
That's a good question. There is, it's not the case for AU-MIC actually. I mean, we might have some ground-based photometry, but we haven't really tried to look at this. I know that this has been actually done for V1298.
Oh, okay.
And the results actually were quite consistent. And you can even try to integrate the fitting of the light curve simultaneously with Doppler imaging.
Oh.
It gives you more constraint on it breaks on degeneracy because this is one of the goals. I can recommend the paper on site.
Cool, thank you.
Before we take the next question, Florian, do you want to start getting ready? Okay, so I think I saw Nathan and then David.
Yeah, can you resolve the stellar inclination with Doppler imaging?
You can, but you're not very precise at it, and it's often quite a generate stuff. But yeah, you can in principle.
Okay.
10 degrees of separation.
10 degrees is pretty good.
It also depends if your star is, inclined at 90 degrees, then it's more difficult because you have some degeneracy, so you're forced to assume some other inclination. If the star is very inclined, then it's much easier in general, more constrained.
Okay.
Yeah, really great talk. You mentioned that you use like maximum entropy regularization to break the degeneracy with the CCF solutions. Do you have a sense if that degeneracy would be lessened if you use the full spectra, or is that like not reasonable to do because it might be dominated by PSF changes or other noise sources?
So I'm not sure what.
Sorry, have you tried moving from the CCF to using the full spectra, for example, because that might break some degeneracies?
I know that there are some prospects on this. I haven't tried. I think that's a great idea. Or, the first step that you could do is basically try just to select some lines that are particularly sensitive to magnetic field or to the inhibition of convective blue shift, and just try to see if you can reconstruct something. I think that's the first step because it's definitely optimized for CCF. Then it might just be a bit slower if you want to go with spectra, but that's definitely something that could be very interesting. I have some reference also there for this if you want.
I'll follow up. Thanks.
Thanks, Baptiste. How you deal with the zero inclination that we have with the sun? So basically, at the end, it doesn't matter if the spot is at the north hemisphere or at the south because you're just considering the scattering the radial.
Yeah, as you say, that first of all, we're definitely radial velocity focused here, this approach, but we just assume an inclination which is erroneous, which is like 80. So some studies assume like something like 60 degrees, but you're forced to assume an inclination which is not 90 degrees because otherwise you have north-south degeneracy and you add degeneracy. It's already very degenerate, so if you can just reduce a bit. And since the inclination is not very precisely constrained, you can show that it's more or less, do not commit too much mistakes on this, I think.
I had a question about what physically does the maximum entropy regularization do to your spot distribution? Because I have heard people say that it essentially pushes the spots to the equator and pushes the spot coverage up.
Yeah, yes, it tends to do this. So basically, there are several ways to do this regularization. In Doppler imaging, you have a Tikhonov regularization method. I know that the maximum entropy tends to push your spot where it will the most likely affect, be able to reproduce your description. So that's true that there is an effect, especially at low inclination, I mean like high inclination like this, low inclination, when your spots start to spread out around the equator. And this is basically what we see on the map when you have like many spots mostly concentrated in the equator. Yeah. This is the problem, the resolution.
Rodrigo.
So if I understand it correctly, are you propagating the uncertainty on the recovered map to uncertainty on the planetary parameters?
Yes.
You are. So why do you need? Because like my understanding of like these regularization methods is to break the degeneracies and get to a unique solution.
Yeah.
But in principle, you could have an uninformative prior.
Yeah, that's true.
If you are propagating your uncertainties all the way.
That's a very good point. Yeah. For now, we went like the easy method was just to say, yeah, we pretty much trust what we obtain, like the spot coverage that we obtain in the fiducial case, and we just want to fix this. And we assume that, I know that I think it might be, the framework would be definitely make more robust at this point. That's definitely true. And you just assume that your chi-square will reflect actually what we really observe, which is definitely 100% accurate.
Thanks.
Yeah.
That's probably just a comment. So thanks a lot. Great work. Sorry, I will remove that. So in fact, what I understand here is that it would be very difficult to really be able to match with what you see with SDO or whatever.
Yeah.
But basically, it gives you a model that is not like a GP or whatever, that is physically driven in the sense that you put spots on the star, what facula, whatever. And again, those reproduce the CCF shape. So it's just a model that is basically physically driven, but then it would be difficult to learn something from the spot coverage at the surface or whatever from those.
So this is actually something that I really want to investigate. So for now, I haven't really started investigating in detail, but what we can do is, like, for example, trying to create actual CCFs using the SDO data only, and just try to apply the code. So the first step, to apply the code to these CCFs and saying like, okay, what does it compare? And maybe then to try just to vary the parameters that you want to take into account. So maybe, I don't know, maybe we can actually learn something about this. But historically in the past, Doppler imaging was mostly used to learn about differential rotation and stuff like this. So maybe we can, we know differential rotation, so maybe I go for it further and stuff. Yeah, it's something to explore.
But so basically, it just gives you one possible explanation for the line profile variations. Yeah. But the underlying assumption, if you use it in the way that Baptiste is describing, is that any spot distribution that's consistent with the observed line profile would give you more or less the same RV. And therefore, it doesn't matter. To some extent, when I was looking at this, I wasn't even looking at the maps that Baptiste reconstructs. All I care about is what the final outcome is.
That's true. That's a good point.
But I think there's an important point, which is that there is a historical heritage to this methodology, which comes from the community that's actually interested in stellar magnetic fields, and that the way in which things are done in that community, we should check, because it's not necessarily the optimal way to do it for this community. Are there any more questions? Otherwise, we can thank Baptiste again.